Jaden, so let's get ready to go.
Okay.
Alright, so good evening to all those that are watching us right now. Sorry we're 15 minutes late, had some technical difficulties there. That took some time to overcome. So,
But we are here, smiling, ready to go.
so pretty. Alrighty. So unless people have questions, which I don't think we've gotten any. Jaden, have you checked the email at all?
I checked 7 and there was nothing. So, as far as I know, there's nothing. I'll double check right now. And there is nothing.
Okay. So if there
Okay.
is nothing, then let's start by doing some more math basics.
Okay.
On Thursday last week, we left off with multiplication and division.
Yes.
And so tonight we're going to start off by going one step further, which is going into exponents and roots, right?
Okay.
So Jaden, if you remember the example last time, right?
Yes, we're using circles and boxes, and you had more circles because you're a thief. Yeah, I think I
Yeah.
remember.
Okay. Well, whatever. So if you remember the example though, where we had me chilling here, and there was this box, right, of 3.
Yes.
Okay. And if you remember, we had 3 of these boxes, right?
Right.
Um,
And we were able to use this example for our multiplication and our division, right? Just because we found out at the end that those are inverses of each other.
exactly. So from there, we wrote this as 3 times 3, right? And we said
Yes.
that was equal to 9. So
Right.
another way to write this is going to be 3 squared, or 3 to the power of 2, also equals 9. And so what an exponent means is you're simply multiplying the same number by itself a certain amount of times. So in this case, we had 3 items and they were in 3 boxes, right?
Right.
And so if let me think here, Jaden. Now, let's say though that we wanted to I'm trying to figure out how to visualize this now and draw this out. You got any ideas?
Visualize the exponent.
Yeah, because this works for 3 to the 2, but as soon as we get 3 to the 3, that no longer is
Yeah.
working quite the same.
Um,
So,
what we would probably have to do is draw more of like a table. So, right, this is our table right now, right?
right.
If we extend that table, we can get like 3 to the third, 3 to the fourth. And what I mean by extend it is we'd have to draw this 3 more times to get 3 to the third, right?
Right. And
So we had
so,
to extend the table, whoop, whoop, have it like this. And in here, there's three circles. Right, this would be 3 to the third. And every exponent you increase, you have to do that last step 3 times, right? So then I would have to do this whole table 3 times for 3 to the fourth, and it just goes, and that's why they're called exponents, right? And that's why we use like exponential growth, because it just gets more and more and more and more, just at this crazy fast rate.
Okay. Yeah. So that's exactly right. Thanks, Jaden, for helping me out there. Another
Yeah,
way to
no
think
problem.
of it is it really is the next step, right? So if you remember, Jaden, in addition, we'd have three, or we had something like, anyways, sorry, for multiplication, which is the next step after addition, you do something like if we had
Right,
3 times 3, um, then we'd do that means we have 3 sets of 3, right? So you do 3
right,
plus 3 plus 3.
yeah,
Um, and
and
this
then
equals 3 times 3, right?
right,
Um, and so then the which also equals 3 to the 2, right? But if we wanted to get 3 to the 3, it would be 3 times 3 times 3 equals 3 to the 3. So it's kind of
yes,
it's kind of that next step, right? So it's going from um, you know simply adding them together. This is multiplication is addition of the same term over and over, and then an exponent is the multiplication of the same term over and over.
right.
Anything
Yeah,
you'd
that
like to
makes
add to
sense.
that?
No, I really like how you showed like that next step thing, right? Like we have the 3 plus 3 plus 3, that equals the 3 times 3, and that equals the 3 squared. And then for the multiplication, just like you wrote there, 3 times 3 times 3 is the same thing as 3 cubed. I thought that was a really good connection with different operations that we are using.
Thanks. Yeah, as so, all of these things kind of are shorthands, right? So it's important to remember that when you're looking at a mathematical equation, what does it actually represent, right? So what if we didn't have threes? What if we
Right,
had x to the third, right? Well, that equals x times x times x.
right.
Okay. Not to be confused with the
So,
multiplication sign, that's an x, not the multiplication sign. But
so Kip, I know a lot of students that I've taught and a lot of just people in general, when we see this x cubed equals x times x times x, some people get confused between 3x and then x cubed. Will you explain a little bit more about that?
yeah, so 3x, right, is going to be equal to x plus x. Okay. So
Okay.
so it's remember it's becoming it's the next step, right? So 3x is you add 3x's together because right here this literally means you have 3x's, right? So you have 1x, 2x, 3x's together. This next
Okay,
step,
so the difference is the multiplication compared to addition, right?
exactly. Um,
Okay.
so if you wanted to, you could write out, you know, um, could you? Let's see here. No, you couldn't. Well, let's think. Um, no, because we don't know how many
Hey,
x's we have. But
um, just for anyone watching, if you have any questions, let us know. Type it out in the chat. Send us an email. Right, we're here to answer any questions that anyone might have right now, and continue.
exactly. Alrighty. Do we want to go into the opposite of a? Do we want to go into the inverse of a exponent and go into roots? Should
Uh,
we jump into that
yeah, I
or
think that's a good. We could do that, or we could do the volume thing that you
okay?
were thinking
So
about.
yeah, so let's hop into volume. Um,
We can save that roots for like next beginning of class.
okay, sounds good. Um, so I wanted to take some time tonight, and it's kind of somewhat involved in the most simple form, using exponents. So I think that that's good that we talked about exponents before. Um,
Right.
but what I want to talk about now is something that's very applicable in our lives on a day-to-day basis, which is, Jaden, volume of containers. All right. So we've got, I'm going to draw this beautiful cube here.
Ooh, that is looking great, Kip.
Thanks, Jaden. Dude, there we go. Not perfect by any means, but
Dang.
it's getting there. Um, so, um, I want to talk about volumes. Dude, I'm looking at this cube and it's doing that weird like optical illusion thing depending on how you look at it. It like switches and
You're like,
flips on
which
you.
way? Which way? Yeah.
Yeah. Which corner is popping out to you, Jaden? Which one's the
um, this one, I'll circle it with a little one. That one's popping out to me.
No, dude, that's in the back corner, man. Oh no, now it's at the front. Okay.
That's
Oh,
funny.
now it's in the back. Okay. Um, so what do you guys think? Is that corner in the back or in the front? Please let us know in the comments below. Um,
Yes.
looking at this, um, the equation for the volume of a cube, by the way, is a three-sided figures where the base equals the height, which equals the length, okay? So if we were to say that this going up here was the height, then this right here is L, and then this right here is B. Those are all the same, okay? It's like a three-dimensional square. Um, but
Okay.
to find the volume of it, it's going to be, for any rectangular prism, is going to be base times height times length, okay? And this equals the volume. Um, so from there, if they are all the same, Jen, choose one. Which one do we want to use, base, height, or length?
Let's just use the base.
So if we can plug in our base for both our height and our length because they're all equal to each other. So we get base times base times base equals volume. And Jaden, from our last little mini lesson, um,
Yeah, that looks like it would be the base to the exponent of 3, right? Or the base cubed.
so we get that equals b to the 3 equals volume. All right.
Right.
So Jaden, do you know what the volume is? What does volume mean?
Uh, from my understanding, it is the available space in an object.
Yeah, exactly. It's how much space is inside, right? How much space something takes up. It's how many
Right.
chunks of little thing there are, right? Inside of
Yeah.
something. Um, and so the reason why I want to go over this tonight is I mainly want to do it from an environmental standpoint, but it's also a very cost-effective thing for both those buying products and those that are trying to sell products and trying to figure out how to maximize your packaging per unit volume, right? Or trying to figure out how to use the least amount of packaging, um, but still have the most volume. And so
Okay.
this is um, something that is really interesting, right? So Jaden, let's say that we want two containers, okay, and I'm not going to draw them 3D because that takes too much time, but we've got one container and we've got another container, all right? And we want
Okay.
the volume, so we'll call this like V1 and V2, and these are equal to each other. And we want these to equal the volume of one bigger container, all right? So that
Ooh,
means
okay.
that volume 1 plus volume 2 is equal to um, volume
Should we just
3.
call that volume 3?
Yeah, okay. So um, let's
Okay.
let's start out by saying that each one of these containers is going to be um, half the volume, right? Because we said that they're equal to each other. So so
Okay.
volume 1 is
That
going to
makes sense.
equal 1/2 of volume 3, right?
Okay. I'm with you.
You following so far? Everyone watching following?
I
Hope so.
am. Yeah.
Um, and so that means so let's solve this now. And I know we haven't gone over roots yet, but maybe this will be a way to go over roots as well. Um,
This will be a sneak peek.
yeah. So we're gonna say then, Jaden, that let's think here. Where do we want to go from here? So we have base of That's how we'll do this. We have base of this is equal to volume 3, right? And then we have,
Okay. So are we saying that they're all cubes
yeah,
or
we're gonna say
is
they're all
just
cubes. We're gonna go with cubes for this
okay.
first illustration because it's the easiest, right? We're just gonna say that all the side lengths are equal, keep things nice and simple. Um,
Okay.
and so then our volume 1 is going to be b to the 3 equals 1/2 of volume 3, right?
Okay. Should we label the B's different?
Yeah, this is going to be b3 and this is going to be b1.
Okay. Just so we don't get confusion happening.
Right. That is a good thing. Um, we got a
We
comment
have a
saying hi.
hi
We
in the
also got a
chat.
comment from Kelsey a little while back saying it's doubtful in the front. I don't know what that means. Maybe definitely in the front, but
Yeah, I'm not sure what that means either.
okay. So I'm trying to think. Maybe I'm This isn't going to get us to where we need to go, but we're going to keep moving forward anyways. So B1 is going to be equal to the cube root of 1/2 of volume 3. Okay.
Okay.
And then B3 is going to equal the square root of volume, or square root of,
Cubed root
or
of.
cubed root of volume 3. Okay.
Okay.
So we are getting somewhere, but we are not quite. Yeah.
So Kip, what you're trying to show is when we do all the math, we're going to have more materials with volume 1 and volume 2 than we have with just volume 3, right?
Right. We're going to have much more.
Right. Okay, just making sure
Yeah.
I am with you with the final goal.
Okay. Thank you. I appreciate that. So should we move on to the next slide here? I think the next thing we have to do from here is go into surface area. Do you agree with me, Jaden?
Yes, that seems like the right pathway.
So for those that don't know, I'm going to draw our cube again here. Let's see how I do this time.
Yeah.
For those of you that's a horrible one, but whatever. Let's fix it up a little bit here. For those of you that don't know what surface area is, it's the amount of stuff that is on the outside of something, right? So it's all of these faces added together, right?
Right.
And so we know for a square, it's going to be the base times the base, because they're the same, equals the area of one of those squares, right? So the surface area, there's 6 faces on a square, is going to be 6 times b squared equals a. Okay?
Right.
From there, we can go ahead and plug in our b's for volume 1 and volume 3. So we have 6 times b squared 1 equals volume 1, right? And then we have 6 times b3 squared equals volume 3. Jaden, do you want to go from here?
I actually don't agree with those two equations because we're talking about area, right?
You don't agree
So don't we
with
need
that?
a different? Don't we need a different letter than a volume? Because wasn't it surface area?
Yeah, thanks. Yeah.
But yeah, I get what you
Yeah,
were.
I appreciate
Going
the
for.
check in there. I definitely do.
Okay. So with the last equations that we had, we have.
Here, I'm gonna change these to A's. Okay.
Okay, sounds good. I'm gonna write down a couple things real quick. B1 equals the cubed root of 1/2. Is it V3? Yes.
Yeah, V3. Yeah.
B3. And then we had the B3 equals cubed root of 1/2 Oh, not 1/2, sorry. It is just V3, right?
Yeah.
Okay. So now we can use this information. We can plug both of these to just have it in terms of our volume to see what the surface area looks like in terms of the volume of the big cube. Is that what you're kind of thinking, Kip?
That's what I'm
Or were you
thinking here.
kind of okay? So that means we have 6. I'm going to use parentheses because this is kind of a lot. So 6 parentheses is another way to represent multiplication. Uh, we have 6 cubed root of 1/2 v cubed. And that is squared. That equals the area, the surface area of our volume 1, or I guess our cube 1 and our cube 2. They will be the same surface area because we know they have the same volume and they're both cubes. Okay. Now we can do the same with uh, the cube 3. So 6 times cubed root volume 3 squared, and that will equal the area 3.
Cool.
Okay.
Okay. Um, so now what I want to do is I want to show how much more we are going to need, how much more surface area we're going to need to get the same volume, right? So we had V1 plus V2 equals V3, right? So we have volume 1
Right.
plus volume 2. So we have these two containers that have these two surface areas, and they're going to be the same, right? So, yeah, exactly.
That's just another way to write that equation because we know the volumes are the same. Okay.
Exactly. So we can go like this, and we can go 2, 6, cube root of 1/2 v3 squared is equal to, I need another parenthesis there, is equal, or not equal to, I'm trying to think here. So we've got that, right? And we want to find the ratio, Jaden, I guess. So we want to find the ratio of A1 divided by A3. Well, I guess this is A1 plus A2, right?
Right.
Divided by 3. To
Okay.
figure out how many times greater, because if you remember back to our division lesson, right, it's trying to figure out how many times something goes into that. And so if we want to
Okay.
figure out how many times greater A1 plus A2 is than A3, we divide it by A3, right?
Right.
And so from there, we can do this, and we can go 6 square root 3 1/2 or cube root, sorry, v3. Now the question is, Jaden, are we going to be able to simplify this and make it not so thanks. Yeah, get rid of that half.
Um,
I
are
feel
we
like
going to
we
be able to
can.
simplify this? Yeah, we could probably simplify this a little bit.
I
Um,
feel like we can cancel out our v3s, right?
right. Well,
I think we can. Because this in here becomes, we can rewrite this
yeah,
out
we
as,
can.
right? We can rewrite this out as 2 to the
So we
6,
can,
and then, yeah, we can cancel out our 6's. But we can rewrite this as the cube root of
yeah,
1/2
1/2 squared
squared times the cube root of 3 to the v3 squared, right? And so this
Yes.
can cancel like that. The 6's can cancel. And we get left with 2 to the cube root of 1/2 squared. And that looks like good math to me. Right?
Yep.
So
I think so.
I'm
And that
just
would be
trying to...
like over 1, right?
You're right. Thanks. Going to the next page, let's just analyze this real quick. So we got 2, and I'm going to rewrite this. This is something you can do in exponents. We've got to the 1/2, and you can put this to a anyways, you can put that to a fraction like that. And should we just... Oh wait, I did this backwards. My bad. This is 2 over 3. So the root goes underneath and the exponent goes on top. And I'm trying to think if there is a way to simplify this more without using a calculator, but I don't think there is. So
Yeah, I think that looks good. Do you want me to
I'm
solve
doing
what
it.
that equals?
I'm doing it right now on a calculator. You're more than welcome to do it as well to double check me. So it equals approximately 1.26. Okay.
Yeah, I got the same.
And so what that means is that for every
What? Oh, I was just gonna say for every like 1 meter of the volume 3 that you would use 1.26 meters of the other.
Right. So
Right.
it's 1/4 larger, or 25% more material is used in the sense of a cube.
Yeah.
Okay. 25% more materials used if you have a cube that's half the size.
Right.
And so anyways, if now that we've solved this, we could, looking at it now, knowing this, if we had a cube that was 3 times, or we had 3 cubes that was 1/3 of the size, it would be 3 to the 1/2 to the 2/3, like that. Or not to the 1/2, that'd be a 3. And so on and so forth.
Right.
And so it may not look like it noticing it from this, but this is going to get bigger and bigger the smaller and smaller it goes, right? So if you have a container that's 1/3 of the volume, 1/4 of the volume, 1/5 of the volume, it's going to get smaller and smaller. Now we used a cube because that way we only have one variable to deal with, right? Which is the base. But also you'll learn eventually in calculus and stuff that a cube is the most efficient shape for the amount of surface area, well, one of the most efficient shapes for the amount of surface area to volume, right? Which means that this is the most efficient outcome. If we were to have a rectangle, that 1.26 number would actually be even greater. And we know that most things that we get at the
Right.
store are not packaged in perfect rectangles. So,
Yeah.
are in perfect cubes. Um,
Imagine just the grocery stores are all just perfect cubes, just lined up.
dude, I honestly don't know why they're not. Like, do you know how much more efficient that is as far as like stacking and putting things together? Like, you could put everything just literally right next to each other and on top of each other. It would be amazing.
Yeah, that would
Um,
be nice. Your gallons of milk, they're just cubes.
dude,
That'd be
actually, I believe it's
a
Sam's
funny
Club.
sight.
They just started doing that with their milks. I mean, it's not a perfect cube, but they now are rectangles, like almost perfect rectangles, and they barely have a spout coming
Oh,
out of the
really?
lid. Yeah. So,
Huh.
anyways, um,
Nice.
so guys, I know this was a long, lots of math explanation, but what it does tell you is that please go buy bulk so that you're cutting down on waste. And if you're starting a
Yeah.
business,
If you're
ship.
trying to get those like 6 Pop Tarts, get the 12. Come on. A
Yeah,
little bit more
just
money, better box, more Pop Tarts. Win, 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 win.
win, 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 win. The other one that I think of is goldfish, right? They have those giant boxes of goldfish, and then they've got the little small pouches. Get the giant box.
Oh, yeah.
And we know you'll probably go
This
through them in the same amount of
lesson,
time as the small one, but
yeah. This also can help you with your wrapping paper, right? If you're busy wrapping a bunch of presents, uh, instead of giving your friend 3 different small boxes, put them all in one box, wrap that, you use less wrapping paper.
right.
Boom. And that is math magical, Kip.
Dude, I totally agree. Hey, I think we've solved this one too. Thanks for the reminder.
Yes.
All right. Jaden, is there anything else we want to talk about? I mean, we could go to a real world problem, use one of these things that we've, uh, come up with. I mean, we could
Yeah,
Google.
do we want to just throw in some numbers with cubes just to make it, I guess,
Yeah,
so those
we.
people that don't understand variables, they can just see like actual tangible numbers?
Yeah, we could definitely do that. I'm wondering. I mean, part of me wants to look up like, you know, I mean, they're more complicated shapes, but I'm just wondering if we could maybe look up really quickly like, height of, I don't know, different. We could look up different volumes of or different shapes for say like a soda bottle, right? And look up like the smaller ones versus like a 2 liter and just treat
Oh,
it like a
yeah.
cylinder. Or we can just do it with cubes and plug in numbers. Either or is fine by me.
Um, let's do a cube because that's what we just did,
Okay.
and we only have like 5 minutes, so we don't have to look up extra stuff for a cylinder.
Sounds good. You don't know the surface area and volume of a cylinder, Jaden?
I know the volume
Yeah,
because
me
that's
too.
just the area of the circle times height.
Yeah, I'm not.
Surface area, I think
I
it's like area of
it's
the circle times 2
yeah,
plus the area of a rectangle.
but it's a
Because if
rectangle
you,
that's wrapped around, right? So
yeah,
you gotta somehow figure out that. I guess that if you think about it, that rectangle would be.
The circumference
Yeah, so
of the
it'd be
circle.
2 pi
Sorry, I
r,
dropped something.
2 pi r times height.
Yeah. So
We
I
figured it
mean, we
out.
could figure it out, but
But yeah, okay, so what numbers do you want to use?
let's use this cube. It's not going to be a cube, it's going to be a square, but all the sides of the cube are the same. Let's call this side length 2. I don't know. Make it kind of easy. Okay.
Okay.
Um, and then if we have another one this same
Well, wait,
size,
Jaden,
so I
don't we want
guess we.
to? So if we already know the side length, um, then I mean that's what we solved for, right? So are you gonna? We were saying the volumes were equal to each other.
All right, that's sorry, I didn't really clarify. I'm saying we have two cubes with side lengths of 2, and we're gonna find the volumes of that, find the third volume, and then we're gonna have to find the side length of that.
Okay. All right. Sounds
Does
good.
that
That makes
work?
sense. Yeah, that works.
So that means our volume is 8, right? 2 cubed is 8, plus 8 equals 16 for a volume.
Okay, so you did, just to clarify, it's 2 times 2 times 2 equals 8, right? 2 times 2 times 2 equals 8. And so then you did 8 plus 8 equals 16.
Right.
Okay.
Okay. So right away we can find the surface area of these two, right?
Right.
Because we have that length of 2.
Mm-hmm.
Okay. And then we can also find the side length of our big cube. Um, should we divide and conquer? Do you want to find the vault or the side length of the big cube, and I can do the surface areas, or vice versa?
Um, I can do the surface areas,
Okay.
the smaller ones. Does that work?
Sounds great.
I want to watch you do more math. I don't want to do more math. I'll come and help you in a second here, because hey, that's here. All right, you right there. You need more space. I'll go down below. Okay, so we've got.
Oh, that's funny. Okay. Um, oh, I have to find the cube root of 16. I didn't give myself good numbers.
No, he didn't.
Whoops.
My numbers were super easy, so I'm already done over here. But
Yeah. Um,
wait,
it is
Jaden, you have a.
about 2.5.
Is that 3 supposed to be down here?
Huh?
That's supposed to be like that.
Um,
You had a 3 like.
volume equals a base cubed, right? So 16 equals b cubed. Oh, yeah, I was missing that 3 also,
Oh,
because
okay.
that's
Never
the
mind.
third.
I got confused. You're right. All right.
Yeah,
Sorry.
I get you now. Um, volume, it is about 2.5. Do we want to use exact numbers, or do we want to estimate?
Um, it's about 2.5. Let's use 2.5. I mean, remember, Jaden, we did come up with this ratio here too, and so we can prove that that
Right.
ratio is right. But so if we do
Yeah.
2.5 and then we square that and we times that by 6, that equals, I think this is about what, like 12.5 or something like that, I think.
Um.
Maybe that's wrong.
You said time. Um. We get about 38.
Okay, so if we do
Okay.
48 divided by 38, what does that equal?
48 divided by 38. Is that what you? Yep. That is just about. So it's 1.263.
Hey,
So
we
yep,
did
just
it!
about our 1 point. Dude, look at us.
Dude, that is math magical.
Heck yeah.
Um, and we solved that. All right, so quick recap. Going through this. Um, this top number is how much surface area or how much stuff we would need to make the volume if we had it divided into two separate containers. And that bottom one is how much, this one right here, is how much we'd need if we had a single volume, right? So again,
Right.
looking at this, you can use it for all sorts of different things, wrapping paper, whatever. You're going to save cost and you're going to be much more sustainable if you try to package, wrap, whatever in bigger quantities than smaller quantities.
That
And
is a wonderful thing about surface area and volume.
yep, it sure is. And so, Jaden, are you going to go buy big things now or small things?
Dude, I think whenever I go buy some boxed cereal, I'm gonna get the family size.
Dude, that is a good idea, Jaden.
Yes.
Okay. Anyone got any questions for us or are we signing off?
We'll have this awkward silence, but it's not very awkward because we're pretty cool.
We are pretty cool.
Uh,
You're more cool.
Dude, you're the most cool.
All right, I'm ending in 3, 2, 1. Goodbye.
Audio.